This is the demo for College Algebra Lesson 16. You'll note that there are no preview exercises for this lesson. So today we're going to briefly review equations of lines. We're going to learn how to create linear models using linear regression for real-world data. So in 1995, there were 246,855 alternative fueled vehicles, or AFVs, in the U.S. And in 1997, 2 years later, there were 280,205. If we measure time in years since 1995, translate the given information into two ordered pairs. So 1995 is year 0, and there were 246,855 AFVs. And 1997 would be year 2, when there were 280,205. Okay, so I want to find the slope passing through these two ordered pairs. So slope is change in y over change in x. So we just have to subtract the y's and subtract the x's. So 280,205 minus 246,855. That is 33,350 over 2 minus 0 is 2. And we get 16,675. Now the units on that are going to be y units over x units. So my y units was AFVs. Okay, these were all time, comma, AFVs. Okay, so AFVs per, my x units were time, so year. 16,675 AFVs per year. So once you have the units on there, it's much easier to interpret the slope. And you can say that the number of AFVs was increasing by 16,675 AFVs each year. Okay, D is explain the significance of the y-intercept in the context of this story. Be sure to explain both coordinates. So a y-intercept is a place where you cross the y-axis, okay, where a graph crosses the y-axis. And when you're on the y-axis, your x-coordinate is 0, right? We went left or right, none at all. So we just stayed here and went up or down to get to a y-intercept. So I actually know the y-intercept, the point on the graph where x is 0, was given here. So my y-intercept is 0, comma, 246,855. Okay, and to interpret it in the context of the story, we would say in year 0, or 1995, which is 1995, there were 246,855 AFVs. E, use your slope-intercept equation to predict the year when there were 510,000 AFVs. So my slope-intercept equation is y equals mx plus b. We have already calculated the slope to be 16,675, and b is 246,855. I want to know when there will be 510,000 AFVs, and AFVs is y. Okay, these are all year or time, comma, AFVs. So x is time, y is AFVs, so I'm going to replace the y with the 510,000 to solve for the x, which is the when. So 16,675x plus 246,855, and we solve for x by subtracting the 246,855 from both sides, then dividing by 16,675. So we get x is approximately 15.7, which is years after 1995. So I'm going to add 1995 to that, and we get the year 2010. So we could say in 2010. Use your slope-intercept equation to predict the number of AFVs on the road in 2003. So they're giving me a year, which is an X value, and this is 2003, which is 8 years after 1995. So I'm going to put in an 8 for X. So I have Y equals 16,675 times 8 plus 246,855, and I get 380,255 AFVs in 2003. So the actual number of AFVs in 2003 was 510,000, which means that the number we predicted was an underestimate. This is way lower than the actual number. So this is underestimate. If we assume that the number of AFVs in the US increased by precisely 16,675 vehicles each year, the scatter plot of the data would look like this. Okay, so it's a perfectly straight line. You can draw a perfectly straight line through those data. Okay. We would call that a perfect correlation. But usually when you're modeling real-world variables, as is the case here, we get data and a scatter plot more like this graph. Okay, it's not a perfect line. So all the data don't fall in the same line. They're not exactly linear, but they do all seem to fall near the same line, even if the correlation isn't perfect. So don't worry about it. Even though the data are not exactly linear, we can still find an approximate linear model for the data, often called a line of best fit. So here's the real-world data with a line drawn through the 2 data points that we gave in 1A of this problem, or earlier in this lesson. So we had 0, 246,855, and 2, 280,205. So I have this point and this point. Those are real-world data points, but I also have 8 more data points. So if I just connect points A and C, if I just draw a line through points A and C here, and I get the line y equals mx plus b, we figured it out earlier, okay? It doesn't do a very good job of capturing what happens up here, okay? It's sort of, the points are sort of diverging from the line. And if I used 2 different points instead of A and C, what if I picked I and J and draw a line through those? Very different line, okay? And if we all picked 2 points in the data, we just get this mess, right? So how do we decide which of these many lines we've drawn is the best one, okay? Or is it even a line that goes through 2 points? I want to come up with a line where all the data are as close as possible to it. This semester, we're going to let a calculator or computer find that for us. If you take a statistics or calculus course, you'll be able to do this yourself. So the equation for the best fit line or regression line is graphed below, and its equation is 35,443.28x plus 216,437.82. So all the data are very close to it. Looks like I have 1 point that's even on it. Other than just looking at a scatter plot and seeing that a line seems like a reasonable model, like oh yeah, it looks like all the data are sort of clustered around a line, there is a way to quantify the strength of a linear trend. It's called the correlation coefficient, and it measures the strength and direction of the linear relationship between 2 variables. It's always a number. We denote it with the letter R. It's always between -1 and 1. When you're at -1 or 1, that means perfect correlation. +1 means all the points fall on a line that has positive slope. If you have r equals -1, all the points fall on one line, but that line has negative slope. So when r is positive, that means positive slope. Negative r means negative slope. And if you have an r between 0 and 1, that means that there's a best fit line and the points are kind of clustered around it. When r is 0, you can barely see a line of best fit. Like, is it horizontal? Is it this? Is it that? It's kind of impossible to fit a line to a random scatter of points. So here's a few samples. This one is 0.33. There is a linear correlation. They're all sort of clustered around a line of positive slope like that. This one is much better correlated than this one. So the points are much more clustered. When you draw a line, all the points are closer to it. Okay, and then 0.98 is even better. They are all tightly clustered around a line like that. So my R values are going from closer to 0 to closer to 1 to exactly 1 if they all land on a line. And then the next row here are just negative R values, which means the same thing as the positive, but the slopes are negative. So this one's very close to 0, but it's got a negative slope, so it's even hard to eyeball. What is the line of best fit? Something like that. This one's much clearer. This one's even clearer, and then this one's perfect. All the points lie on a single line. It's very important to note that strong correlation does not mean that X causes Y or Y causes X. Okay, correlation does not imply causation.